Hi, this is the third FRQ on the AP Physics C extra credit, and I will be walking you through it. So here we're given a different sort of question, and it's not typical, as we're asked to design an experiment instead of just doing some math and physics. So we have to really think for this one, and we got to know what the experiment does, and it says it investigates the conservation of mechanical energy involving a transformation from initial gravitational potential energy to translational kinetic energy. So, before we get started, let's go over our physics facts. We're going to need to know these: our kinetic energy formula, Ke equals 1/2 mv squared, and our gravitational potential energy formula. Potential energy equals mass times gravity times height. And then we're also, this one's not quite so obvious, we're going to need to know this kinematics formula. V final equals V naught plus AT. So now let's get back to the question. And it asks us to label the pieces of equipment we're going to need to use the experiment, to conduct the experiment, but I think it's actually easier to do B first, figure out the procedure, and then we can determine what we need to conduct that procedure. So I wrote it out, and keep in mind there are, I'm sure, many other ways to conduct this experiment that are totally correct and that would get full credit. This is just what I thought of. So this is not the definite only solution, but it's just the first thing I thought of. So I thought, first, measure the mass of the objects with the electronic balance. So we're going to need the electronic balance and the objects of differing masses. Hold one object h meters above the ground and drop the object from rest. And then use the stopwatch to measure the time it takes for the object to fall to the ground. And then repeat the experiment until 10 trials have been completed with different heights, and different objects. So we get different masses. Okay, so now we can go back. We have B answered. Let's check that off. Now, let's do A. So A, we know we need our meter stick to measure the height. We know we need the electronic balance to measure the masses. We're going to need a stopwatch to measure the time it takes. And lastly, we're going to need a set of objects at different masses. Okay, so now we have A done. Now on to C. We need to conduct some calculations. Okay, well, let's first do let's draw a picture. How's that? So this is the meter stick, and then there's going to be an object of height h. Height h. Okay, and then the experimenter will have a stopwatch and be measuring time it takes to fall. Okay, so now let's calculate the initial gravitational potential energy. So I'll say G P E I, and that's going to be mass of the object times gravity times the initial height. Okay, now let's calculate final gravitational potential energy. Well, that's going to be, hang on, let me write it up, PF. And that's going to be our mass times gravity, that stays the same, times 0, because we know the object falls to the ground. So its final height is going to be 0. And that's just going to equal 0. Okay, great. Now we need to know our initial kinetic energy. So I'm going to move over here. I. And that's going to be 1/2 times m times v naught, v initial, squared. And, oops, we know the object starts from rest. We explained that in our experiment. So if it starts from rest, we know our initial velocity must be 0. So that would mean initial kinetic energy equals 0. Okay, so now we just need to find our final kinetic energy. Well, final kinetic energy isn't quite as simple because we need to find our final velocity. And how are we going to find our final velocity? Well, that kinematics formula we figured out, or we went over earlier, is going to come into play. So here, to calculate our final velocity, we're going to do v final equals v naught plus acceleration due to gravity, acceleration in the y, times our t. Well, we know that equals 0, our v naught, because it starts from rest. So v final, and a, it's in free fall, so that's going to be negative g, negative 9.81 meters per second squared, negative g t. Great. So now we can calculate our final kinetic energy. Well, that's going to be 1/2 m times our final velocity, and our final velocity, negative g times t squared. And that's our answer. So now I'm going to clear. And now we have to go back to doing some thinking. So after your first trial, your calculations show that energy increased during the experiment. Assuming you made no mathematical errors, give a reasonable explanation for this result. So take a second to think about it. I've thought about it and I have an answer, but take about 15 seconds, try and come up with one on your own, or pause this video. Well, my initial idea, the one that came right, like kind of sprung to me, the low-hanging fruit, is that it's difficult as humans to do anything perfectly, but to perfectly drop an object for rest, because it's hard to have a hand that's totally stable. So the experimenter, his hand might have been moving, might have moved down a little, so it may have not been totally released from rest. So its initial velocity may have been a little more than 0 if he threw it down, if you will, because the experimenter may not have released the object completely from rest. Okay, so that's an answer to D. And again, there's many different ways to answer this problem, so feel free to put a different answer down. That's not the definite answer. Okay, so question E. On all other trials, your calculations show that the energy decreased during the experiment. Assuming you made no mathematical errors, give a reasonable physical explanation for the fact that the average energy you determined decreased. Okay, so the opposite of D. Include references to conservative and non-conservative forces. Okay, well, take a second, think about your physics knowledge, and maybe pause the video, and we will resume. So the answer that originally I thought of was that non-conservative forces such as air resistance, friction, they may have converted some of the mechanical energy to heat or maybe sound energy, and then that would decrease the kinetic energy that's measured right before the object hit the ground. So, in other words, some energy dissipated from those non-conservative forces. So the total energy decrease. So the work would be negative. Okay. So great work, and that's just how I would answer FRQ number 3. And keep in mind that there are many other ways to answer it. Thank you.